Hello everyone. Today I'd like to tackle a fun little graph theory exercise where we have a group of 17 people in which each person has 4 friends and friendship is mutual, and we want to show that there are 2 people in this group that aren't friends and that have no common friends. So if you've tackled this type of problem in the past, you know that you should look at graphs that represent this situation, and especially the graph in which each person is represented by a vertex and the friendships are represented by edges. So 2 vertices, so i.e. 2 people, are going to be connected to each other if and only if they are friends. Okay, so now in this situation, what does it mean in terms of graph to have 2 people that aren't friends and have no common friends? Well, let's take 2 such people. Okay, we know that they aren't friends, so we cannot have an edge like this. And we know that they have no common friends, which means that there cannot be a third vertex such that they are both adjacent to it. Okay, we cannot have this. That means that the distance between these 2 vertices in the graph, so let's call them vertex number I, for instance, vertex number j, means that the distance from I to j is greater than 2. Right? Because they cannot be 1, they cannot be connected to each other, and they cannot be 2 because that would mean that they have a common friend. Okay? So if 2 people aren't friends and have no common friends, their distance in the friendship graph is at least 2. And of course the converse also holds. If the distance between 2 people is at least 2, well then since the distance no, actually not at least, it's strictly more than 2, of course, yeah? So if it's strictly more than 2, then they can't be friends because otherwise the distance would be 1, and they can't be common friends because otherwise, well, they can't have common friends, otherwise the distance would be, well, 2 at most. So this is equivalent. So let's just write I and j satisfy the condition if and only if in the friendship graph the distance between I and j is strictly greater than 2. Okay? So what are we going to do? Well, we're going to suppose by contradiction that for any couple I and j, well, their distance is at most 2. And so, well, let's just now take a look at a specific person. So let's say person number I, and try to see what the friendship graph might look at when you suppose that for all ij, the distance between them is at most 2. Okay, so when we suppose this and we try to draw our graph, so we have person number I, we know that they have exactly 4 friends. 1, 2, 3, 4. And now we look at the friends of the friends. And since we know that for any person j, well, their distance to I must be at most 2, it means that when you look at the person, the friends, and the friends of the friends, well, you must obtain everyone, right? There can't be anyone else that lies outside of that. But now look, suppose that we have 3, suppose that we are in this situation. where basically these guys are not friends with each other, they're only friends with other people that we haven't introduced yet in the graph. Okay, well in this situation, how many people are there in this new graph? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. There are 17 people in here, okay? Which is exactly the number of people in the group. So actually, this means that, for instance, we cannot have any friendships like this, okay? Because if these two guys were friends, well, then they wouldn't be able to be friends with all of these three guys because we know that they're friends with only 4 people. And so that would be 1, 2, 3, 4, 5, so that's not good. This guy wouldn't be able to be friends with one of these guys. And so basically, instead of having 17 people at distance at most 2 from person number I, well, we would have strictly less than 17. So this is not possible. We cannot have this type of friendship, okay? In a similar way, of course, these two guys cannot be friends with the same guy. Like suppose if we're not in this situation, but we're in this one here, where this guy is a common friend with this guy and this guy, then once again we took a person away, and so well, there's someone else outside of here that is at distance strictly more than 2 with person number I. So that's not fine. So we really have to have this type of structure. Okay, now let's try and formalize these remarks that we've noticed on the structure in terms of cycles in our graph. So first of all, the shortest type of cycle is a free cycle, which is a triangle. Okay, so let's look at triangles. Can we have triangles in our graph, in our friendship graph? Well, first of all, the fact that there are no triangles in this graph is of course not enough to say that there are no triangles in the friendship graph, because here we haven't written down all of the friendships. Like there are many friendships missing from every one of these guys. Why are they missing? Why didn't we just draw them out? Because in this case we really cannot have any idea of the structure of the friendships, you know. We cannot really know the structure of the graph without showing additional results. But when we look at the triangle, well, for instance, suppose that here we have person number I. I mean, I can just be anything. So if we take I to be a person that's in a triangle, well then look, 2 of his friends are themselves friends. But this means that we would have something like this, or like this, which we just showed a couple minutes ago is impossible. Okay? So we cannot have triangles in our graph. And the same thing is actually going to work for 4 cycles. So no triangles. What about 4 cycles? So basically squares or rectangles or whatever you want to call it. Well, once again, if you take this person to be 1 in the 4 cycle, well then, okay, there are 2 friends here. They're not friends with each other, but they're friends with the same guy. Okay, and we just said a couple minutes ago that 2 of person I's friends can never be friends with the same guy. So no 4 cycles. Okay, that's already pretty nice. What about 5 cycles? So 5 cycles look like this. Well, this time we can't rule out the possibility that a 5 cycle exists, right? I mean, here we just have this guy's friends, then they both have two different friends, and this is just saying us that, for instance, this guy is friends with this guy. This would create a 5 cycle in our graph. Well, this is entirely possible. So we can't rule out that 5 cycles exist. In fact, I mean, they must exist, because when you look at this guy, I mean, this guy for now is only friends with him, so we know that he's friends with 3 other people. And well, he cannot be friends with anyone over here because that would create a 4 cycle. He cannot be friends with this guy because that would create a 3 cycle. I mean, in any case, we've already used up all of the friendships of these guys, so of course this is impossible. So he must be friends with one of his peers over here. Okay? Of course, he cannot be friends with this guy because this would be a 3 cycle. He cannot be friends with this guy for the same reason. So he must have friendships like, for instance, here, here, and so you see that every time you add a friendship, you're adding a 5 cycle to our graph, like 1, 2, 3, 4, 5, and 1, 2, 3, 4, 5. Okay. So you've got a certain number of 5 cycles that are obtained by just adding all of the missing friendships to our graph. So how are we going to use this? Well, this is where there's a little trick, which is not entirely obvious as to why we would do it. Well, we're going to try and count the 5 cycles. So namely, we're going to try and find, how many 5 cycles contain I, okay, contain vertex number I, right? Because if we manage to find this, then we should be able to easily find the total number of 5 cycles, because I was taken to be arbitrary, so you can easily imagine that there will be some sort of symmetry where like every vertex is contained in the same number of 5 cycles, okay, which will let us calculate the total number of 5 cycles in the graph. Okay, so every 5 cycle in which I is basically can be obtained by adding some of these missing friendships here, right? So how many missing friendships do we have to? Well, do we have to add? Well, there are quite a lot, right? Because for every one of these guys, in every one of their missing friendships, we have, of course, a different 5 cycle, except no, they're not actually all different. Of course, when you're taking, for instance, when you're taking this guy's missing friendships, okay, let's add 1. Well, then you're also drawing a missing friendship for this guy. So you're actually counting every 5 cycle twice. Like basically I'm saying, okay, I'm adding 1 5 cycles, that one 5 cycle that contains person I by drawing this line here. But this also counts as a 5 cycle that I obtained by starting here and drawing this line here, okay? So by just counting all of the missing friendships, I would be counting every 5 cycle twice. So I need to divide the number of, so we basically just need to be careful. Instead of summing all of the missing degrees, we need to just sum the number of edges that are missing. So how many edges are missing? Well, we're missing, so we said, so we have 3 times this number of guys, 1, 2, 3, 12, divided by 2, okay? Yep, this should be correct. So it's equal to 3 times 6, so 18. So by just adding all of these missing friendships here, we obtain 18 5 cycles that contain person number I. Why aren't there any more? Well, simply because any 5 cycle that contains person number I must contain one of these guys, right? Because if it didn't, then it would only contain, well, these people over here, right? Because there are no people outside of this graph. There are some edges that we didn't draw, but there are no vertices because we already have 17 vertices. And of course, well, this guy does not form a 5 cycle with these 4 guys, right? Like you need to go through one of these guys, and hence 2 of them, right? Since we determined that an edge here, well, that the only missing edges are edges that connect 2 of these. Like these are the only 5 cycles in which I can appear. So there are exactly 18 5 cycles that contain I. So this is independent of I, which is really nice. Because it means that we're going to be able to find the total number of 5 cycles quite easily. So let's just write 18. So how many 5 cycles in total? Well, we said that every person was contained in 18 5 cycles. So if you count like that the number of 5 cycles, you get the number of people, so 17 times 18, right? But when you're counting in this way, you are counting every 5 cycle multiple times. Since every 5 cycle contains 5 vertices, in this way you're counting every 5 cycle exactly 5 times, once for each vertex. So the actual total number of 5 cycles is 17 times 18 divided by 5. Okay? And what is this equal to? Well, it's actually equal to something that's not an integer, right? And so this is why we wanted to count the 5 cycles, and this is where we get sort of lucky, because if this were an integer, well, we just have found the number of 5 cycles and then that's it, right? Like we need to continue looking for a contradiction somewhere else. But thankfully we get lucky because this is not an integer, right? Like here there's a 5 in the denominator, but 5 is not a prime factor of either 17 or 18, so it does not divide the numerator, and so this is a contradiction. So what does this mean? What had we supposed at the beginning? We had supposed that for any pair of people, their distance in the graph was at most 2. That means that there exists 2 people that are at distance strictly greater than 2 in the graph. And these 2 people, well, they aren't friends and they don't have any common friends. So we've solved the problem. No, I mean 2 factorial also, I guess, but I just wanted to write this as a as an exclamation mark. But hey, thankfully 2 equals 2 factorial, so we were fine in any case. So yeah, this is a nice little problem. The solution is not that hard to understand, but I feel like coming up with a solution is really hard. I mean, looking at the friendship graph is a really natural first step. That doesn't pose any real challenge. But then trying to, well, of course, you're going to try and understand the structure of your graph, but looking specifically at 3 cycles, 4 cycles, 5 cycles, that's not obvious. And also having the idea to count the 5 cycles for basically no reason whatsoever is also, I guess, is also a bit of magic. But yeah, it just all works out. It just all works out because we get a non-integer number of 5 cycles. And actually, this sort of extremal problem, like where we have exactly the maximum number of people, like for a given number of friends, like we have a maximum number of people that are at a, like basically if we wanted to generalize this, instead of, instead of talking about friendship, you just talk about the distance in a graph. Like you try and find a set of vertices that all have same degree, so same number of friends, and are at most a certain distance from each other. So here the distance is 2, but in general you could take something else. And the interesting thing is there are some situations in which it works. Like you can find a graph that has a maximum number of vertices while having this distance condition and the fact that they all have same degree. So there are some cases where it works, but this particular case with distance 2, 17 vertices and degree 4 per vertex doesn't work. So yeah, there's a pretty cool theorem, I think, that that tells you in which cases it's possible and in which cases it's not. So if you want to look at that, it's always an interesting problem in graph theory, I feel like. So yeah, that's it for today.